This video is going to focus on the size of atoms and ions. It's very difficult to say where one atom stops and where another begins because there's not a hard outer shell around the atom. So scientists have got several ways for measuring the size of an atom. Most of these methods depend on the fact that the one thing within the atom that's easy to measure is the nucleus. So if you can have two atoms next to each other and measure the distance between the two nuclei, you can measure the size of the atoms. One method is called the non-bonding atomic radius. That happens during the collision of atoms. So when two atoms bump into each other, you look at that time period where they're the shortest distance apart. You can measure the distance between the two nuclei. Half of that is the radius of one atom. Another method is called the bonding atomic radius, and that's when two atoms are bonded together. You do the same thing. You measure the distance between two nuclei. Half of that distance is the radius of the atom. This is the method that we're going to refer to. So when I say atomic radius throughout the course, I'm talking about the bonding atomic radius. That changes as you go across the periodic table in a predictable manner. You can see here, this is trying to show you that it decreases as you go from left to right, and it increases as you go down the periodic table. The reason it increases as you go down is because each time you go down a row on the periodic table, you're adding an energy level. So as you add energy levels, the atom gets larger. The reason it decreases as you go from left to right is because as you go from left to right across the periodic table, you're adding a proton to the nucleus each time. So that's increasing the nuclear charge. That's increasing the amount of pull that the electrons are feeling. So as you go from left to right, those additional protons are pulling the electrons in tighter. So the trend is that atomic radius increases as you go down and decreases as you go from left to right. There are some exceptions to the trend. One of the more obvious ones occurs right here. When you go from palladium to silver, you can see that it increases. But what we're discussing is the overall trend. So this arrow represents increasing atomic radius on the periodic table. And notice that it's the opposite of the z-effective arrow that we discussed in the last video. This data can be used to predict the bond length between two atoms. So for example, if I were trying to predict the length of the bond between a carbon and oxygen atom, I would add up their two radii values. When I do that, I get a value of 1.42. If you were to then go and measure that actual bond length, it's not going to be exact, but this does give you a good rough estimate for what that bond length is going to be. I also want to point out that the unit for this value is in angstroms, and 1 angstrom is the same thing as 0.1 nanometers. The data we just looked at was for neutral atoms. Now we want to look at the size of ions. So what happens to size when atoms take a charge? This is measured by looking at the distance between atoms that are located in ionic compounds. What we want to be able to do is compare the size of an atom without a charge to the size of the ion that has a charge. What you'll find is that this is different if we're dealing with a positive charge, a cation, or a negative charge, an anion. In the table to the left, all of the yellow represents neutral atoms. The red are ions that are positive, and the blue are ions that are negative. Let's look at the cations first. All of these cations have lost electrons. So the outermost electron is removed, That means the whole atom is going to drop in energy level. So here's your neutral atom, your cation is much smaller. Here's your neutral atom, your cation is smaller. The opposite happens when something becomes an anion. In order to take a negative charge, you have to gain an electron. So the atom actually gets larger when it becomes an ion. And you see that in the pictures. Here's the neutral, here's the negative ion, and you can see that it's much larger. So you should recognize that a cation is smaller than its parent atom, and an anion is larger than its parent atom. Sometimes we are asked to compare the sizes of several ions. Generally, these will be in what is called an isoelectronic series. That means that these are a series of ions that have the same number of electrons. I'm going to explain this by showing a series of examples. Consider oxygen. Oxygen has 8 protons. If it has a charge of -2, that means it has gained 2 electrons, so it has 10 electrons. Okay, fluorine has 9 protons. If it has a charge of -1, then it has gained 1 electron and has a total of 10 electrons. So these have the same number of electrons. They are isoelectronic. Sodium has 11 protons. If it has a charge of +1, that means it has given away an electron. It has 10 electrons. So hopefully you're seeing that there's a trend. All of these are going to have the same number of electrons. We can predict which one of these will have the largest ionic size. It's based on the number of protons. Ionic size decreases with an increasing nuclear charge. So as you add protons, the size decreases. So in this example, aluminum with a charge of +3 is the smallest, and oxygen with a charge of -2 is the largest. And this goes back to Coulomb's law. As you add protons, you're adding positive charge to the center of the nucleus. That's going to have the ability to pull the electrons in tighter. So your take-home point from this slide is that as in an isoelectronic series, as you add protons, you decrease size.